get started. So I can make multiple videos, and then I'll upload these videos onto a YouTube channel playlist that is just for this class. And after we've done a couple, I'll show you where to find them. That way, if you're ever missing, you can see them later. Also, if someone gets COVID symptoms and is gone for 5 days, I might still stream it on Teams at the same time making the recording so that all of the year's lessons are available. And I've had students come back and say, oh yeah, once I went off to university, I was learning that again, and I actually went back and watched some of the videos that you had done in class. Now, I was saying, you have seen the concept of a limit before. Probably the first place that you saw a concept of a limit was in geometric sequences and series. Do you remember adding up an infinite amount of numbers? For example, if I start 16 blocks away from the wall, and I walk half the distance to the wall, I'll walk 8 squares. And then if I walk half the distance again, I'll walk 4 squares, then 2 squares, then 1 square, then half, then a quarter. Will I ever get to the wall? No. Because I'm always, whatever distance is left, I walk half that distance to get closer. And yet, in your geometric sequences unit, you did this. Do you remember adding 8 plus 4 plus 2 plus 1 plus a half plus dot, 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 dot? It was an infinite series. An infinite series where the R value, its geometric, was 1/2, and you had a formula in grade 11 that said the sum of an infinite series is term 1 over 1 minus R. Now, if I do that, if I put term 1 as 8 and R as 1/2, and I simplify that, that says 16. That if I started 16 blocks away to begin with and continued to walk half the distance each time, and I did that for an infinite amount of times, they're saying that the answer is 16. But in our logic, if every time I look at the distance between me and the wall away, and I only go half closer, theoretically, I should never get to the wall. So how is it that the answer to this is 16 if in reality cutting the distance in half every time, you'll never get there? Well, we call the 16 the limit. We get so close to 16 that at infinity, we basically say you're so close to 16, you're basically at 16. But if you stop anywhere along the line and say, how close are you now? You're not at 16 yet. Go a little, do it for another million times. How close are you now? You're not at 16 yet. But we get closer and closer and closer to 16. You saw the idea of a limit when you did graphing, especially graphing with asymptotes. With an asymptote, your graph is getting closer and closer and closer to that value, but not equal to that value. So calculus looks and uses the concept of a limit. The first unit that we're doing is looking at what is a limit and how to evaluate them. And then our next units will go into calculus. And there's sort of 2 main branches or types of calculus: integral calculus and differential calculus. In all calculus courses, you learn differential calculus first and integral calculus next. Historically, integral calculus can be traced back to like 350 BC. Famous mathematician Archimedes was using this idea of figuring volume under different shapes or areas under different shapes by continually making smaller and smaller rectangles. So for example, if you had some funky shape like this, and you wanted to find this area, he would say, well, if you made 2 rectangles, that'd be an okay estimate, but you'd have too much. But if you made smaller rectangles, oh, that's a better estimate of the area. Still a little bit too much. But if I kept making my rectangles smaller and smaller and smaller and smaller, and kept adding up little tiny rectangles along the way, I'm going to get closer and closer to the actual area. And what Archimedes called it was a method of exhaustion. It sounds like not the kind of method you would like to use in math. It's like by the time you're done, you're going to be barely breathing and gasping for air, because he kept doing these smaller and smaller and smaller and smaller, and then you'd have to add up, oh, this time I'll add up 1,000 rectangles. Ooh, I got pretty close. I'll add up 2,000 rectangles. But what he was getting at was this idea of a limit. The smaller I make the rectangles, the closer I get to the whole area. Now, interesting is that this is the second idea of calculus you study, and it was sort of dates back to 350 BC. The first area of calculus we tend to say goes back to either Newton or Leibniz. Okay, now this is a totally different period of history. This is 17th century, so that's not that long ago. And it was discovered, and they say by two people. So the way that we would think today is that, oh, they worked together and they figured it. No, 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 no. Science didn't work that way back then. It was, you didn't share things with other people. And in fact, if you would go to the dates, and I'm not sure on the dates exactly, but if you look at the dates when they discovered them, they were like years apart. So someone might say, well, if Newton discovered it 15 years earlier than Leibniz, then he discovered it first. But if he didn't share that information, and Leibniz discovered it totally independently, that's why it's attributed to either of them. And we use some of Newton's notation still and some of Leibniz's notation. So they both had things that were advantageous to how they did it. Now, if you would have studied mathematics 100 years ago, your English textbook would always say Newton discovered calculus. And the German textbooks would always say, no, no, Leibniz discovered. It's all on a matter of historical intricacies that way. Just by the way, what was life like as a scientist that time? Much different than today. Today, if you find something out, you share that information, but you publish it so that it does get attributed to you for discovering it. Back then, scientists didn't like each other. They didn't share their stuff. When they found stuff, they didn't tell anybody. They hid it. They kept the knowledge for themselves because that would give them more power over someone else. Newton was head of the Royal Society. The head of the Royal Society before Newton, I believe, was a scientist called Hooke. Newton did not like Hooke at all. And after Hooke died, Newton destroyed all of his work. So there's even pictures of him. Now, that's what I recall. So there's some interesting historical things that's happening in that time. So a preview to limits. One of the things that we have to do and be able to do well when we're doing limits is to be able to factor. Right? You factored lots, we're going to factor some more. But we're going to factor some things in ways that maybe you haven't factored before and sort of stretch your abilities and your limitations as you have done in the past. So we'll start off with some straightforward factoring that we've done. The greatest common factor. Okay, if you see something in common in each of the terms, you can factor that out. It's going to be a factoring technique that you've done before. We'll do it again. I'll do the first one here. I notice in all three of these, I have the same factor, the variable h. I can pull that out. There's no numbers in common, so I'd be left with 3h squared plus 7h minus 1. And then I would look inside and I'd have to ask myself, can I factor this further? Because it's a binomial, maybe I could do it's a trinomial, maybe I could do 2 factors for it. In this case, I can't, and this is factored completely. Try that second one on your own. So what will happen sometimes in class is I will do an example or two, and then I will give you time to try one on your own. And I'll put up the answer, and you can check to see if you were able to factor it completely. If you want to work ahead on the next ones, you can. All right, how did you do on that one? All right. So the common thing in all of them was the 2, the p, and the q. Factoring trinomials, if we have 3 things like this, what we're looking to is if we can break it up into 2 factors. And some of you come from French immersion, some of you come from English classes. In English, when we multiply something out, we use an acronym FOIL. So if you start taking, so by the way, this one, if we factor this, this is x and x, that'll give you x squared. And to give minus 24, we would need a plus 12 and a minus 2. This is a tricky one because 24, you're more natural, probably because of your times table, to think 6 times 4. And you're like, yeah, 6 times 4, and 6 plus 4 makes 10. But in this situation, the 12 and the 2, one has to be positive, one has to be negative to give you that negative 24. And in English, we use the acronym FOIL because when you multiply and you draw all the arrows, you multiply your first ones, so you have an F. You multiply the outside one, so you have an O. The inside one, so you have an I. And the last one, so you have an L. And so if you're coming from French immersion, you might hear somewhere along the line someone say, oh, you just FOIL it. And you'd be terribly confused because you're like, I don't know what that means. Okay? It's just an acronym that's taught in grade 9 and 10 to make the distribution easier. But the key, the reason I bring it up is when you're factoring a trinomial, there's a pattern that always happens. There's a pattern that your first ones, if we're using the same language as the acronym, the first ones always are this one, the last ones are always this one, and your outside and inside will always combine to that middle one. And you can use that as a hint for figuring out how to factor. So in this one, the fact that the first one's a p squared, I know that it has to be p and p. That's the only option that's going to work out nicely. The last one is a 45. So I know these last 2 numbers have to make 45, but there's some options there. 9 and 5, 15 and 3. But I need to make a 4 when the outside and the inside are combined. So there's some mental math here. If I do 9 and 5, my outside is 5 and my inside is 9. That could make 4. If I need a negative 4, I need the 9 inside to be negative 9 and the outside to be plus 5. And after you factor, you should always do the mental math to check to see if I multiply this out, if I distribute everything appropriately, do I get the right answer? So there's a couple for you all to try. Some of them Some of them you've got some more complicated techniques. And in grades previously, you might have learned some grouping technique for factoring. That's great. If you still know how to use it, go for it. Some shortcut methods. I tend to find for a lot of the factoring that you do after grade 10, if you think about, these are going to be my first ones, these are my last ones. This one is complicated because that first one's a 6. So if I wanted to put numbers here, do you see that it could be complicated? Because it could be 6 and 1 or 2 and 3. And if you choose the wrong one and try it first, nothing's going to work. For me, factoring this one, I actually say, oh, but the last one is a 3. Why don't I start with that one? The only possibility is 1 and 3. That's the only way I can get a 3 with whole numbers. And now I can start to do a little bit more mental math with the first ones. If I want to get 11, I'm going to put a 3 here and a 2 here, so my outside is 9 and my inside is 2. With all the arrows, if you imagine the arrows, there's the inside, there's the outside. That's going to make 9a and 2a. If I add them together, I would get 11a in the middle. A quick multiplication here to check, and I see everything matches up. 3a times 2a, 6a squared. 1 times 3 is 3. 9a plus 2a makes 11a. So again, I'm still multiplying it out and factoring it. I'm doing a lot of mental math at the same time. Once you get into higher level calculus and stuff, you want to be able to factor quickly and do a lot of mental math that way. But as a reminder, okay, how many of you have in the past would have done, okay, I'm looking for a product of 18 and a sum of 11. Do you remember doing that for factoring? Okay. If you're using that, you're looking, well, what two numbers give me a product of 18 and a sum of 11? The numbers are 9 and 2. You would then rewrite the middle 11a with the 9 and the 2. This is called the grouping method for factoring. And then once you have those 4 terms, you look at the first 2 and say, what's a common factor between 6a squared and 9a? I can take a 3a out, leaving me with 2a plus 3. There's no common factor in the next one, so I could take out a 1 and also have 2a plus 3. If those are the same, which they are, you can then factor out the 2a plus 3, leaving you with the 3a plus the 1. So that's a little bit of a longer way of factoring that one, but if that's a method that you remember and you like, that's great to use that as well. I'll let you try the second one. I'll put the answer up in a bit. So there's the answer. Again, if I was factoring this one directly as mental math, I would start with the 2x squared because there's only one possibility. It has to be 2x and x. Whereas the last one I started with the 3 because it only had one possibility of 1 and 3. The 35, well, it could be 7 and 5 or it could be 1 and 35. So we have more than one possibility there. But once I've got the 2 and the 1 here, now I can do some mental math with the 35. I need to get a 9. Okay? So if I look at how things are spread out here, if I put the 7 here and the 5 here, the outside is 14, the inside is 5. 14 and 5 make 9. If I need a positive 9, I would need a positive 14 and a minus 5. So I use the outside and the inside arrows to check this number. But once I have that, I'm going to do a quick check. Are my first ones still 2x squared? Do my last ones make negative 35? They do. And do the other arrows work out to give me 9 in the middle? Yes. So anytime you can factor something directly, it's good, one, because it takes less work and to show your work because you've just got the answer there right away. Two, sometimes students will make notation errors while they're doing longer methods, and depending on the course, sometimes you get deductions for those notation errors. You guys didn't write a grade 12 pre-calculus exam. The grade 12 pre-calculus course has a list of 10 errors that if students make on the exam, you have to take off a half a mark. If you were in my class, I marked down the errors as you did them. Some of you collected quite a few. All right. Next type of factoring. In English, we call it a difference of squares. Why? Well, the difference part means subtraction. There's a subtraction sign in between. And squares means that both the first number and the last number are perfect squares. So 9x squared is 3x times 3x. 25 is 5 times 5. So when we factor this as a difference of squares, we have 3x and 3x, 5 and 5, and 1 is positive and 1 is negative. In fact, if you do the arrows for this one, if you distribute, you can see that the first one is still give you the 9x squared. The last ones give you the minus 25. And your outside and the inside, because one is plus and one is negative, they cancel each other out. It's basically the same idea of factoring a trinomial. It's just that there's a term missing because there's 0 of them after you simplify. Try that one. This one involves your exponent laws from grade 9. Sometimes those ones make it harder to see that the first is a perfect square and the last is a perfect square. Not yet. I'll show you how to do it. All right, there's the answer. And now I'm going to expand your worldview of difference of squares a little bit more than what you've had in the past. I'm going to tell you that if you want to apply these rules of difference of squares, you can even factor some things that aren't quite differences of squares. For example, x squared minus 3. X squared is a perfect square. We've got the minus for the difference part. but 3 is not a perfect square. That does not mean that you're not allowed to break the rules a little bit and factor this. If I follow the same rules here, I would have x and x. One would be plus, one would be minus, but what would go there to make it work? Square root of 3. Kind of broke the rules a little bit because 3 isn't a perfect square, but doesn't this work? If you multiply it out, it works out perfectly. So this is the next stage that we start to do. We start to say, okay, these are the rules I've learned in the past. How can I manipulate them a little bit and be a little bit creative to make them work? And there will be some questions that we get in assignments where it's like, yep, you will have to be creative. You will have to be sneaky to see if you can figure out a trick to make this work. And then we get questions that have multiple steps for factoring. Why is it multiple steps? Well, this first one, it's a trinomial, but before we try to factor it as a trinomial, you should always check if there's a common factor. Because in this one, I can pull out a 3. That makes my life a lot easier. Because now what's left to factor inside is something easier to factor than what was original. And that's another one of my favorite trinomials for factoring because you see the 6 and you see the 5. Did you think 2 and 3 first? I always do. And it ends up being 6 and 1. Just like the 24 with the 10 and with the 12 and the 2 and the 4 and the 6. Okay, second one as well. Do you see there's a common factor of a 2p? Oh, man. That's like, I should have changed the numbers because I have a childhood comic. You ever watch that 2p? And yes, just got into my head right as I factored that out. I should have picked different letters. Now you're bringing back memories? You watch, oh, not good memories. Watched it too much. And then this is a difference of squares, so it can be factored even further. I got a challenge one for you. Which one? Factor this one for me. Completely. Did you try it? No. Come on, it's not bad. All right, how many people got step 1? x6 plus 1, x6 minus 1. Excellent. How many people saw that that wasn't done? That this is still another difference of squares. So you would have x to the 6 plus 1 x cubed plus 1, x cubed minus 1. And then, oh, I didn't mean for it to be this mean because we haven't got there yet. But this is the difference of cubes. And we're going to learn how to factor that this year too. So these ones, oh, this is a sum of cubes. Oh, I shouldn't have done this question this way. Difference of cubes, we're going to learn that you can factor this to be x squared plus x plus 1. And you're going to also learn pretty shortly, you can factor this middle one I did not mean for it to be this complicated to factor. I had, in my head when I made the question, I thought I'd be tricky enough just to end here. But then I realized I had a sum and difference of cubes. Don't worry, that's coming up in our notes. It's interesting because differences of cubes and sums of cubes is one of the topics that often when you get to university professors think, oh, you should know how to factor this from high school. But high school teachers never teach factoring differences. Well, we do factor cubic equations in grade 12 in the polynomials unit. In the polynomials unit where you do the factor theorem and the remainder theorem and synthetic division. Remember that? Not really? That's okay. It's different. Don't remember those words because they're obviously in English rather than in French. Okay. So now we're going to get to some factoring that is completely new that you have not done before. When you have fractional exponents or negative exponents, the technique you can use is to factor out the smallest exponent as a common factor. So in this first example, the smallest exponent would be an x to the negative 2. If I take an x to the negative 2 out of each term, it's a little bit complicated because you're like, I don't see any x to the negative 2's in that first term. Okay? So this is what you got to imagine. I pulled out an x to the negative 2 because that's the smallest exponent. What would have to be here so that if I distributed it, I would get a 1? X to the negative 2 times an x to the 2, can you see that that would make 1? So if I take an x to the negative 2 out of this, an x to the negative 2 out of this, an x to the negative 2 out of this, basically the way that I would do this factoring is I'd write my x to the negative 2 out in front, and then instead of factoring it out, I would imagine, okay, I have another arrow going here. What number would be here so that when I multiply, I get 5x to the minus 1? And then I'd imagine what number would be here. That one's the easiest, I think, because you can see there was an x to the minus 2 there. You take it out, now you just have 6. But in the second one, can you see that you would need a 5 to get the 5? And when multiplying exponents, you've got your exponent rules all the way back from grade 9. Multiplying exponents means you add the exponents together. What exponent would have to be with this x so that when I add this exponent plus the negative 2, I get a negative 1? It would have to be a 1. So when factoring this out, this is what I'm left with. But the strategy that we used was sort of like I took it out, and then I thought, what would I need to multiply in each space? I think that's an easier way to think of it than imagining, oh, I have a 5 to the x minus 1. I pull out an x minus 2. It's like, that hurts the brain a little bit to imagine that. Yes. That's right, because when you factor something out, you are dividing, right? Plus 1. So factoring something out is the same as dividing. So by taking it out there, taking it out here, taking it out here, you could use your exponent laws that way as well to find out that you have an x to the 2, 5x to the 1 and the 6. And then this can be factored. Now we got our 3 and a 2 for factoring that one. Second example. First thing I would notice is that there's a common factor of 3 in each of them. So you're always looking for common factors because taking that out makes your life easier. Then with the fractional exponents, I look at all of my fractional exponents, and the one that's the smallest would be the x to the negative 1/2. So that's what I would factor out. See if you can fill in what would be missing. I've got it up there. You can check. Did you get it right? And then from there, now we're left with a regular trinomial inside the brackets, which is our basic factoring that we can factor completely. So this is new. This isn't in any grade 12 curriculum. It's not in any IB curriculum. But it's using things that you've known in the past, and it's a way of taking an equation and manipulating what it looks like. And a lot of solving complicated math questions is just a matter of manipulating. You're taking one thing, manipulating it to look like something else so that you can work with it. And now you can solve questions like this. Oops. Right? We solve equations. One of the ways that we can solve an equation is by factoring. And in this one, I see there's a common factor of 3. And the smallest fraction is the negative 1/3. So if I pull out the 3x to the negative 1/3, this is what I get. The inside now is easy to factor. And if you're solving it, the reason we factor, the reason that we factor is we change something. Here's an expression where we have 3 things added together that makes 0. Okay? If I make an equation in my head where 3 things are added together to make 0, and I said, okay, guess what I have in my head, you would take you a very long time to guess what I had in my head, because it could be anything. But when we factor, this is the power of factoring, we change something that's adding to something that's multiplying. And this is very powerful because if you're multiplying, no matter how many things you're multiplying together, and the answer is 0, What do you know about one of the factors? One of the factors has to be 0. There's no way you can be like, unless you make mistakes, like 7 times 6 times 3, 0. No, that's not right. You can get 0 if you make mistakes, but the only way things multiply to be 0 is if one of the factors are 0. And this is the power that you have to check each one. If this is 0, then x would be 1. If this is 0, then x would be negative 5. What about this? This is never 0. Why is it never 0? Well, do you remember your negative exponent laws? Can you see that that's the same as 3 over x to the positive 1/3? Negative exponent laws say you just move the power to the other side of the fraction. So if it's in our numerator, we move it to the denominator. And the only time a fraction is equal to 0 is when the numerator is equal to 0. And my numerator is 3. Last I checked, 3 is never equal to 0. And so the only solutions to this one are x equals negative 5 and x equals 1. All right. Now, this is the factor theorem, synthetic division, the words that you didn't know from French. Okay? For those of you taking grade 12 pre-calculus right now, you've never seen this before. So it will be new for you. But if we were trying to factor a cubic function like this, it's possible that it could equal 3 factors. And whatever those factors are, the 3 last numbers that are there will have to multiply to give you negative 10. That's just the way multiplication works. So if I know that, then there's some possibilities. We could have a 1 here, or a 2, or a 5, or a 10. But it should be pretty obvious that we could never have a 7 here, because then my numbers won't be whole numbers to work out. And if we're factoring something, we're looking at factoring it with whole numbers. Next, something that you learned in grade 12 or about to learn in grade 12 when you get to chapter 1. Okay? The next thing is if these are factors. Okay, I'll cheat a little bit and tell you that, I'll tell you that the answer way down here is x minus 1, 3x minus 5, and x plus 2. Okay? I'm cheating and telling you that that's the answer in the end, because I want to show you something that's important for figuring out how to factor it. If I plug in a 1 for x, can you see that this will equal 0? And 0 times anything will be 0. If I plug in a negative 2, this one would equal 0. And 0 times, doesn't matter what the other ones are equal to, is equal to 0. So when we go back up to the beginning, and we're trying to factor this, and we're trying to figure out, should I use 1, 2, and 5, or 1, 1, and 10? What should be my numbers? We check the possibilities, 1, 2, 5, and 10. These are all the possibilities it could be. We plug them in. So I try 1, I try negative 1, I try 2, I try negative 2, until I get an answer of 0. Mental math-wise, if these are all the possibilities, all the factors of 10 divided by all the factors of 3, if these are all the possibilities, I wouldn't start by guessing and checking with my plus or minus 1/3. I'm going to try with my lower numbers until I find one that works. Try 1, it doesn't work. Because if I plug in 1 for x, it doesn't equal 0, so that tells me that x minus 1 wasn't one of the factors. But when I plug in -1, I do get a 0, which tells us that one of the answers has to be x plus 1. And for those of you that are taking grade 12 concurrently, when we run into a topic like this one that has already been taught in the grade 12 but you haven't seen yet, I can show you where I've already got YouTube videos on teaching that topic. So if you want to watch those on your own and learn it before you learn it in your grade 12 class, that will be fun. So we find one possible root. Can I scroll to here? Is that okay? Once you find one possible root, in the grade 12 course, this is where you used your synthetic division. Is a quick way to divide. We have the coefficients from the original term. The -1. Here, I'll just reenact it to help you remember how this is done. Do you remember that you brought down whatever the term was first? Do you remember that these numbers, 3, 4, -9, and -10, they were the coefficients of the original equation? 3, 4, -9, and -10. You brought down the 3. You multiplied -1 times 3 to get -3. And then you added. 4 plus -3 is 1. -1 times 1 now is -1. And you added, which would give you -10. And then -1 times -10 is +10. And you added to get 0, which is what you expect there to be no remainder because we found it to be a perfect factor. After you've done your synthetic division, you can now rewrite the original equation with the x plus 1 as a factor, and then these numbers, the 3, the 1, and the -10, they tell you what's left in your binomial afterwards. Yes? Yes, x plus 1. And then the binomial part, now you can factor that directly, and we factored this completely. So factoring is going to be a very important skill as we move forward into our equations. And I mentioned it earlier, and we're going to look at it just quickly right now. One of the things that is covered in university but not seen as often in high school is factoring differences of cubes. Did I go too fast? Okay, sorry. I will I'll warn you. No, just please let me know when I do that, because I will warn you that I'm like, ooh, I looked ahead and I saw that factoring of cubes was next, and I like factoring of cubes. So I get excited about going to the next topic too soon. So please let me know. Good? All right. So factoring a difference of cubes could be done using the same technique that we just did in the last question, right? I showed you one earlier, x cubed plus 1, okay? Let's say you had this. Can you see fairly easily that you could plug in a -1 and make it equal to 0? Okay? This means that x plus 1 is a factor. Agreed? And if x plus 1 is a factor, then I could do synthetic division here. The coefficient of the x cubed is 1. There is no coefficient in front of an x squared. There is no coefficient in front of an x. And my constant number is 1. If I'm dividing by x plus 1, I'd put a minus 1 out in front. I could bring this down. 1, multiply, add, multiply, add, multiply, add. And so x cubed plus 1 is equal to x plus 1 times x squared minus x plus 1. And the x squared minus x plus 1 cannot be factored anymore. It's as factored as you can get. So this is using grade 12 pre-calculus to factor a sum of cubes. This pattern, though, that happens will work if both numbers are cubes, as in here, x cubed plus y cubed. It'll always factor nicely this way, to an x plus y, and then you have an x squared first and a y squared last to make them work. When you distribute everything out, a whole bunch of stuff cancels out. In order for it to cancel out, if there's a plus sign here, there has to be a minus sign here. Because if everything is plus signs, everything will be added, nothing will cancel out. Okay? The same thing happens with the difference of cubes. X cubed minus y cubed, you get x minus y as a factor. But since we have a minus sign here, we have a plus sign in the middle for everything to work out. You got an extra? Perfect. So this review sheet, practice questions, you can do the first page now. We have some, we'll end up the sum of cubes and difference of cubes with these examples here. If you're factoring something like x cubed minus 8, and you've got the formula for any difference of cubes like x cubed minus y cubed, can you see that you could rewrite x cubed minus 8 is x cubed minus 2 cubed? So your in the formula, this is x, but this would be a 2. And then you just have to plug things in to make it work. Yes? No, it's just giving you questions for practice. So there's lots of questions there. Some of them you're going to look at and are going to be easy. Some of them you may look at and say, "Ooh, that one's too hard for me." What you want to be doing is you want to maybe try a couple easy ones at first, and then sort of get to the level that is a little bit of a challenge for you. You don't want to jump to questions that are too challenging Some people like to do every single question. If that's you, perfect. Because the more you practice, the more you learn. So in this one, can you see that your x, if you were looking at the formula with x cubed plus y cubed, that your x is a, and your y would be 3b squared. And then when you go to factor it, you would have a plus b, 3b squared, and it all multiplies out perfectly. So I'll give you the last 10 minutes to start working on that sheet. You will find that we do get a fair bit of time in this class to work on examples and practice things. Or you might want to take some time to really, in those last 10 minutes, look over that difference of cubes and sum of cubes because it's new. Sort of see, can I see how this was working? Yes.